This is day 19 of Advent of Cyber, and this challenge is called Wiggles Go Brrr. Spying on Santa. Elfin Skitty was doing a regular sweep of Santa's workshop when he discovered a hardware implant. The implant has a web camera attached to a microprocessor and another chip. It seems like someone was planning something malicious. We must try to understand what this implant was trying to do. We will deal with the microprocessor and the web camera in future tasks. For now, let's try to uncover what the other chip is being used for. The VM that we will use for this task takes approximately 8 minutes to start, so I guess start that now. Okay, so the learning objectives are how data is sent via electrical wires in low-level hardware, hardware communication protocols, how to analyze hardware communication protocols, reading USART data from a logic capture. Welcome to the Matrix. Hardware hacking is often shrouded in mystery and seen as a super complex topic. While there are a lot of in-depth complex hardware hacking components, getting our feet wet is actually pretty simple. Computers today are incredibly powerful. This allows them to build additional features and safety measures into their communication protocols to ensure that messages are transmitted reliably. Thinking about the TCP protocol, which has multiple redundancies in place, it even sends 3 full packets just to start its communication. In the world of microchips, we often don't have this luxury. To make sure our communication protocols are efficient as possible, we need to keep them as simple as possible. To do that, we need to enter the world of zeros and ones. This then begs the question, how does hardware take electricity and generate signals? In this task, we'll focus on digital communication. For hardware communication, we use a device called a logic analyzer to analyze the signals. This device can be connected to the actual electrical wires that are used for communication between 2 devices that will capture and interpret the signals being sent. In this task, we will use a logic analyzer to determine the communication between 2 devices in the rogue implant. The electrical heartbeat. Back to our question, if we have electricity, how can we generate a digital signal? The approach most hardware components take is to simply turn the power on and off. If the power is on, we are transmitting a digital 1. If the power is off, we are transmitting a digital 0. We call these 1s and 0s bits. To perform communication, we simply turn the power on and off in specific sequence to transmit a bunch of 0s and 1s. If we send 8 bits, we are sending a single byte. Voila! We have just performed digital hardware communication. These are the wonderful squiggly lines you would see on a logic analyzer. We can transmit text data by using the ASCII table. Sending the binary representation of each character, we can transmit data. However, it isn't actually just that simple. If we wanted 0 effort in our communication, we would need an electrical wire for each 0 or 1 that we want to transmit. Considering that a single character is 1 byte of data, thus 8 electrical wires, this can become a mess of wires really fast. To make this more efficient, we need to use fewer wires and then have both hardware chips agree to a specific digital protocol and configuration that will be used to transmit data. Let's look at some of the most common protocols and how they work to send data, still while reducing the number of wires needed. Universal Synchronous Asynchronous Receiver Transmitter, or USART, communication, or as it's better known, serial communication, is a protocol that uses 2 wires. One communication is used to transmit, TX, data from device A to B, and the other wire is used to receive, RX, data on device A from device B. In essence, we connect the transmit port from one device to the receive port from the other device and vice versa. What is interesting about this protocol is that there is no clock line that synchronizes the communication of the devices. Without a clock, the devices have to agree to the configuration of communication, such as the following. Communication speed. This is also called the bit rate and dictates how fast bytes of data can be sent. Agreeing to a specific rate tells each device how fast it should sample the data to get accurate communication. While there are fixed standards for baud rate, devices can choose to use any other rate as long as both devices support it. Bits per transmission. This is normally set to 8 bits, which makes a byte, but it can be configured to something else, such as 16 bits. Stop and start bits. Since there is no clock, one device has to send a signal to the other device before it can send or end a data transmission. The configuration of the start and stop bits dictate how this is done. Priority bits. Since there can be errors in the communication, priority bits can be used to detect and correct such errors in the transmission. Once the 2 devices agree on the configuration of the serial lines, they can now communicate with each other. A single transmission is shown in the diagram below on how the ASCII character of S would be transmitted. There are a couple of caveats, however. The devices don't really have a way to determine if the other device is ready for communication. To solve this, some USART connections will use 2 additional lines called clear to send and request to send to communicate to the other device whether it is ready to receive or ready to transmit. Furthermore, to agree upon what voltage level is a binary 1 or 0, a third wire called the ground wire is required to allow the devices to have the same voltage reference. However, despite all this, USART is an incredibly popular protocol in microprocessors due to its simplicity. SPI. The Serial Peripheral Interface communication protocol is mainly used for communication between microprocessors and small peripherals such as sensor or an SD card. While USART communication has the clock built into the TX and RX lines, SPI uses a separate clock wire, separating clock SCK from the data lines allows for synchronous communication, which is faster and more reliable. So the trade-off is adding an additional wire, but we gain a speed and reliability boost. Example of the same S being transmitted using SPI shown below. The clock line tells the receiving device exactly when it needs to read the data line. The two-way communication is also possible, but quite a bit more complex than the serial communication. Essentially, one of the devices is labeled a controller. This is the only device that is allowed to send stock clock signals. All other devices become secondary devices that must follow the controller's clock signal to transmit data back. If two-way communication is used, instead of having a single data line, two lines are used, namely peripheral in, controller out, which means communication is sent from the controller, and peripheral out, controller in, which means communication is sent from the secondary device back to the controller. Using this, the controller sends a clock signal and a command out to the device using the PICO line, and then keeping the clock signal, the controller reverses data back on the PICO line, as shown in the diagram below. There is one additional change that can be made. While there can only be one controller, there can be multiple secondary devices. To save wires and ports, all devices can use the same SCK, PICO, and POCI lines. A fourth wire, called the chip select wire, is used to distinguish the device that the communication is meant for. The controller can use this line to indicate to the specific device that it wants to communicate to, as shown in the diagram below. SPI communication is a fair bit more complex than USART, but having a dedicated clock line increases the speed at which we can communicate and improves reliability. I2C, the Integrated Circuit Communication Protocol, was created to deal with the drawbacks of both USART and SPI communication protocols. Because USART is asynchronous and has the clock built into the transmit and receive lines, devices have to agree ahead of time on the configuration of the communication. Furthermore, speeds are reduced to ensure communication remains reliable. On the other hand, while SPI is faster and more reliable, it requires many more wires for communication, and every single additional peripheral requires one more chip select wire. I2C attempts to solve these problems. Similar to USART, I2C only makes use of two lines for communication. I2C uses a serial data line and serial clock line for communication. However, instead of using a chip select wire to determine which peripheral is being connected to, I2C uses an address signal that is sent on the SDA wire. This address tells all controllers and peripherals which device is trying to communicate and to which device it is trying to communicate to. Once the signal is sent, a data signal can be used to send the actual communication. To notify other controllers and peripherals that the communication is taking place and prevent these devices from talking over each other, a start and stop signal is used. Each device can monitor the start and stop signals to determine if the lines are busy with communication. An example of such data transmission is shown below. Since an external clock line is used, communication is still far more reliant than USART. While it is slightly slower than the SPI, the use of address signals means up to 1008 devices can be connected to the same two lines and will be able to communicate. Now that we understand the basics of hardware communication protocols, we can look to analyze the logic of that rogue implant. Probing the logic. After sending this rogue implant to the forensic lab for analysis, the following circuit diagram is uncovered. Based on the diagram, it seems like there is a microprocessor that's connected to an ESP32 chip. Doing some research, we can see that the ESP32 chip allows microprocessors to communicate over Wi-Fi and mobile networks. So whatever this implant is doing, it was definitely communicating with someone else. If we can intercept the communication between the microprocessor and the ESP32 chip, we will be able to see what commands and information are being sent. It seems like the perfect opportunity for a red and blue team to team up. Elf Forensic and Elf Recon are on the job. The elves realize that these chips probably use digital communication that can be intercepted with the logic analyzer. Looking at the wires between the chips, we see a black wire connected to a pin called GND, and a red wire connected to a pin called VIN. Elf Forensic knows from experience that this would be the ground and voltage in wires, respectively, meaning these wires are used to provide power to the chip. That then leaves the green and purple wires that would be used for data transmission. Seeing they are connected to RX0 and TX0 pins, Elf Recon can deduce that this refers to the transmit and receive lines of USART communication. Hence, we are pretty sure that the protocol used for the communication is USART. Armed with this information, the elves connect the probes of the logic analyzer to the green and purple wires before powering on the implant. Immediately, superfast signals are seen on the analyzer. The elves create a logic data dump from the signals, and McSkitty is asking you to investigate what is actually being transmitted. Analyzing the logic. In order to analyze the logic data dump, we will need to use a logic analyzer called Salay. Start the machine attached to this task, which will open an in-browser Windows machine where all the required tools have been installed for you. Once the machine is loaded on the desktop, double-click the Logic 2 application. Okay, so we're on the desktop of the box, and we go to Logic 2.4.2, and this will load the Salay logic program. Okay, with it open, we can now continue. So we need to import the logic data dump to start our analyzer, so select the Open a capture option and select the Santa file that's on the desktop. Go back, File, Open Capture. Then on the desktop, we select Santa. Okay, it's now loaded the file, so let's continue. So if you hold left control and use the mouse wheel to zoom out a bit, you should be able to see the digital signals. Go here, go control wheel. Okay, there we go, we can see the signals. Okay, so let's carry on. D0 and D1 refer to the digital channels of the two lines that were probed. A0 and A1 refer to the analog data from the probers. Hover your mouse over the first stick line on D1 channel 1 and use left control and the mouse wheel to zoom in again. You should be able to see the entire signal transfer. So D1 channel 1. Okay, you need to zoom in way further to be able to see what's happening. Okay, so it's at 50 ms. Okay, I might need to zoom out a bit. It's at 3 seconds, 600 milliseconds plus. Okay, there we go. Now we can see what's going on here. What is very interesting from this screen is that you can see how the analog voltage data corresponds to the digital signal that's seen. Looking at the A1 channel 1 versus D1 channel 1, you can see that there are slight breaks in the analog data that have been corrected in the digital channel. Now that we can see the digital signal, we can look to use Logic Analyzer to read the contents of the data. Click on the Analyzers tab to the right, so that is here. Since we know the protocol is USART, let's look to configure an async serial analyzer for both channel 1 and channel 0. Let's configure channel 1's analyzer first. So if we were true hardware reverse engineers, we'd first have to figure out the rate at which data is being transmitted, as well as a specific configuration such as parity bits and frames. However, to keep this simple, Forensic Elf has already discovered this for you. Alter your configuration to match the following and click Save. So we need to do async signal, and this is for channel 1. The bitrate is 4800. 8 bits per transfer, 1 stop bit, no parity bit, least significant bit sent first, non-inverted, and normal. So once saved, we can see that the data is being analyzed. Click the little terminal icon and we can actually read the data being transmitted. So we can click Save, and the little terminal icon right here. Cool, we can see the data there. We see the initialized sequence of the serial line and then 3 lines of data being sent. This doesn't mean anything yet since we are only seeing one side of the data. In order to see the other messages, we need to add another analyzer to channel 0. Click the plus icon next to analyzers and add another sync serial analyzer with the same configuration except for channel 0. So we will do that. Go plus async serialize channel 0 and save. We can go to the terminal thing here and we've got more information. Once added, click the trash icon in the bottom right to remove all terminal data. Once done, click on the 3 dots next to each analyzer and select Restart on both of them. Your terminal should show you something like this, which it's already showing for us. Now we are starting to piece together the information. It seems like the microprocessor is establishing a session with the ESP32 device to allow communication to the control server. We can now see the full discussion between the two devices. The processor asks the ESP32 to reboot its connection to the control server. The ESP32 is happy to oblige, but requests a security code to be sent to allow connection to the control server. Once the security code has been transmitted, the ESP32 allows the microprocessor to negotiate a new baud rate to be used for the communication. Interestingly, once this new baud rate is accepted, we cannot read the rest of the output. However, since we intercepted the baud rate, we can now simply edit our channel 0 analyzer to a new baud rate to read the rest of the communication that was sent. Go and make this change to get your flag. So if we go to here, we can edit it and change it to 9600, and if we go to here we can change this also to 9600. We see down here we've got the flag, try hack me, hacking hardware is fun, so we can copy that, and the flag which is down here can submit that. So let's look at the other questions. What device can be used to probe the signal before sent on electrical wires between two devices? So that is a logic analyzer. USART is faster than SPI for communication. That is a nay, because the SPI is the clock wire, which allows it to be more reliable. USART communication uses fewer wires. That is a yeah. USART is faster than I2C. I think that's a nay. I2C uses more wires than SPI. That is a nay. SPI is faster than I2C. That is a yeah. What is the maximum number of devices that can be connected on a single pair of I2C lines? That was 1008. What is the new baud rate that is negotiated between the microprocessor and the ESP32 chip? That was 9600. Okay, so that is day 19 of Advent of Cyber completed. If you like this video, make sure to like and subscribe.